Kafka on S3 and how AutoMQ integrate with Iceberg. Take it away, Xinyu. Okay.
Okay, sure. Thanks, Kami, for introduction, and give me some seconds. I will share my slides. Okay. Okay. Hello everyone. Thanks for joining us today. And let me quickly introduce myself. And I'm Xinyu Zhou, co-founder and CTO of AutoMQ. And AutoMQ is a cloud-native Kafka built on object storage. And before starting AutoMQ, I need messaging and streaming products at Alibaba Cloud. And I have also been deeply involved in the open source community, and I'm a member of Apache Software Foundation and a PMC member of Apache RaconQ and the Apache Incubator. Right now, I am mentoring a new project called Apache Omoro, which is a lakehouse management system for modern data lakes. So if any of these projects interest you, you are welcome to join the communities. So today I will walk you through the key challenges we faced building AutoMQ and how we made Kafka run efficiently on object storage, and how we are bridging the streaming and the tables with seamlessly integration into systems like Apache Iceberg. So let's get started. So what exactly is AutoMQ? And at its core, AutoMQ is a cloud native alternative to Apache Kafka. We have completely reimagined Kafka's storage layer and replacing it with cloud storage services like AWS S3. And this allows us to leverage the scalability and the cost efficiency of object storage while maintaining Kafka's
On S3.
reliability. Sorry?
Please.
Okay. Yeah. And here is the best part. And AutoMQ is totally open source. You can find it on GitHub. So just start and clone it. And this project has gained traction globally. And we have almost 7,000 stargazers worldwide and more than 70 core contributors from different companies like AutoMQ, Singapore Grab, Zhihu, Reload, Tencent, and many others are actively involved. And also, it's not just a community project, it's a production proven, and AutoMQ is already handling over 100 GB per second in the real-world deployments. So if you are passionate about the AutoMQ, Kafka, and cloud native systems or open source projects, we would love to join us. We would love for you to join us, and any contributions to AutoMQ are welcome. Yeah. So all right, before we dive into the challenges, and let's quickly walk through the architecture of AutoMQ. AutoMQ architecture is very simple. It only has one component, the broker. But to understand how it works, we can think of it in three parts. Now, first, at the bottom, we have shared cloud storage. All data is stored in object storage like S3. And the great thing about modern cloud storage, like it's built for durability. For AWS S3, for example, it uses erasure coding to deliver more than 11 lines of durability. So which means we don't need to replicate data ourselves. So the storage layer already guarantees it. So no more worry about the data loss. Uh, and in the middle, we build something called S3 Stream. It's a lightweight library that let us run Kafka-style partitions directly on object storage. We replaced Kafka's local storage with S3 Stream, and which fundamentally changes the architecture, from shared nothing to shared storage. And this shift makes the broker completely stateless. So which is a big deal because now brokers don't own any data. So they are just compute workers. So which means we can deploy AutoMQ like any other stateless service. Super flexible and easy to manage. And yes, we can even run each on spot instances to save costs. And because everything is decoupled, so we can automate the whole system. We build two smart controllers. One handles auto scaling, it watches the load and scales the cluster in and out automatically. The other handles auto balance. It moves partitions around to avoid hotspots and keep performance smooth. So in short, so we took Kafka and moved the storage to the cloud and made broker seamless and added smart automation. So now we have a cloud native, elastic, and fully automated streaming storage system. So now let's go into the key challenges we had to solve to make this work. Let's get straight to the first challenge, the Kafka compatibility. So we can imagine as Kafka's API is to streaming data, what SQL is to static tables. So it's a language every data streaming application already speaks. So if we want to run Kafka on S3, we cannot just say, hey, we speak almost Kafka. Customers will run way faster than our Java GC post, right? So what we didn't do, some projects try to rewrite the whole Kafka protocol. It sounds heroic, right? But Kafka has thousands of APIs, multiple versions per API, and plus the heavy features like transactions, idempotent producers, and even compacted topics. So trying to re-implement all that and keep up with upstream is almost impossible. So what AutoMQ actually did, we kept the Kafka's computer layer untouched. Instead, we rewrite a new log segment implementation to replace the Intel storage layer with S3 stream. So it's basically you can imagine that it's still Kafka, but it have a brand new cloud-native storage engine. So this gives us 100% API compatibility and fast, no effort adoption of new upstream Kafka features. Okay, all right, let's talk about the next challenge, latency. So we all know that Kafka is very fast. We are talking about single digital milliseconds, right? But for object storage, a simple put API maybe can take hundreds of milliseconds. So that's a huge jump. So now we can imagine that if our customers are moving from Kafka to AutoMQ, if the latency suddenly goes from 5 milliseconds to 200 milliseconds, so they would have to retest everything, their concurrency, their downstream systems, the whole pipeline. So that's not just annoying, it breaks compatibility. So here's what we did. We added a persistent read-ahead lock. We call it a wall layer on top of the object storage. So the data first writes to the wall storage. It's fast and durable, and then in the background it uploads to S3. So the producer can get a quick egg, and the latency drops back to single digits. And also the wall storage is very flexible. You can like use high performance EBS storage or low latency S3 Express or Azure Premium Blob storage or even standard S3 if you are okay with a bit of more delay. And so now we have the same durability and much better speed and low surprise latency specs for users. And the next challenge is about IOPS. We know Kafka is built around partitions now. We can imagine that each partition will write its own data files. So, but when you move this model to object storage like S3, this model becomes very expensive. So that's because every put API to S3 will cost you money. Like in AWS 3, 1,000 put requests cost $0.005. So it sounds small, but if you scale it, imagine that if you have 1,000 partitions and each one writes every 100 milliseconds, so that's 10,000 writes per second. So at this rate, you are spending 0.05 per second. So if we add up to over a month, it will cost you like $100,000 per month. So it's just an API cost. So that's not just expensive; it's unaffordable, right? So what's the fix? In AutoMQ, we resort how data is written to the object storage. We introduced two types of objects. The first one is stream set objects and stream objects. So here is how it works. So instead of writing each partition's data separately, we batch multiple partitions data together. So when the batch reaches a certain size, we write it as a single stream set object to S3. But if one partition is super active and generates a lot of data quickly, we can also write it directly as a stream object. So no batch needed. So this way we can significantly reduce the number of API calls. So instead of thousands of small puts, so we do fewer larger uploads. Yeah. So, all right, let's talk about the next challenge, data fetch efficiency. So, for Apache Kafka, with local disk, Kafka relies on OS page cache. So it's very simple and effective. But when we move data to object storage, we cannot depend on that anymore. So we need our own cache for object storage. So in AutoMQ, we build two caches for two different jobs. The first is the local cache. It handles the recent data, and when a broker, sorry, when a broker, oh sorry, so when a broker gets a message, it writes to the wall and puts a copy in the local cache. So this way, consumers reading the latest data get it super fast. So just from the memory, low S3 needed, right? So second, the block cache. This one handles historical data. If data isn't in the local cache, we check the block cache. Also, it pulls data from S3 in batches and uses prefetching and keeps hot historical data in memory. So just like a smart file system, right? So to sum up, we have low cache, it's for hot data and the recent rates and the faithful cleanup. For block cache, it's for cold data and we have smart loading and ARU-like management mechanism. Yeah. So together they keep reads fast and whether you are reading the latest message or something from the last week. Yeah. So the next is about metadata management. So in AutoMQ, every object in S3 has metadata, right? So if we store all of it in Keyrafts, the metadata grows too fast. So that's a scalability issue. So we tackled it in two ways. First, we reduce the number of objects by compaction. We merge small stream-set objects and stream objects into larger ones. So fewer objects means less metadata to manage, right? Obviously. So second, we move the metadata of Keyrafts and into the objects themselves. So we designed a self-described S3 objects. So each carries its own header with key information, like which streams it contains, their office range, and the positions in the object file. So we even combine multiple objects into composed objects, which can include secondary indexes for faster lookups. So how about the results? So now Keyrafts only needs to store the object ID and the stream ranges it covers. So everything else lives in with the data. So we keep metadata lightweight and scalable and fast. The next one is about traffic management. So in the cloud, every EC2 instance has a network limits. Let's say like 100 megabytes per second. So that's not too much when you are running a high throughput system like Apache Kafka. So here is a key difference between traditional Kafka and AutoMQ. In Kafka on disk, the only network traffic we manage is from producers, consumers, and replication. So all data stays local. So there is no traffic to or from external storage. But for AutoMQ on S3, it's different. We have additional traffic from access and object storage. Like producers write data to S3, and historical consumers read data from S3. And also compaction reads old data and uploads the new compacted files. All of this adds up and can easily hit the EC2 bandwidth limit. So we built a global traffic limiter in AutoMQ based on the token bucket algorithm. It controls all the network traffic load-wise, so we never overload the instance. And we don't just limit, we set priority for different traffic types. Like producer write traffic gets the highest priority. So when the network is busy, the lower priority tasks like compaction are sorted or delayed. So that way we protect the critical paths like the incoming writes while still handling background work like compaction. Yeah. So, all right, let's talk about the next challenge, zero cross-AZ traffic. So mud-AZ deployments are standard in modern cloud architectures. They are essential for fault tolerance and high availability. But here is a catch. Cross-AZ traffic is very expensive. For example, AWS and GCP charge for data transferred between AZs. For example, every GB of cross-AZ traffic will cost $0.02. So this might not sound like much, but when you scale up, it adds up fast. Actually, in traditional Kafka on the cloud, network costs can account for over 60% of your total expenses. So you will pay for the producer and the consumer traffic across AZs and the replication traffic between brokers in different AZs. And for AutoMQ, we have already solved the replication cost by leveraging the cloud storage durability. We don't need to replicate data manually because S3 or other object storage handles it for us. So, but how do we eliminate cross-AZ traffic for producers and consumer sites? So the answer is rack-aware routing. So for consumers, it's very simple. All the reads go through the local broker. Since all data is stored in S3, so every broker can access any partition's data. And the rack-aware router will ensure that when a consumer fetches the data, it always connects to a broker in its own AZ. So this broker then retrieves the data from S3 locally in the same AZ. So basically, there is no cross-AZ traffic for consumers. So for producers, it's a bit tricker. So imagine a producer in AZ2 writing to a partition whose leader is in AZ1. So instead of forwarding the data directly, the AZ2 broker will write the data to S3 locally in AZ2 and then send the lightweight RPC to the leader in AZ1 to assign an offset. So then retells the offset to the producer. So the actual data goes to S3 within the same AZ. There is no cross-AZ transfer, only a small metadata RPC crosses runs, so it's very cheap. So I want to talk with you about the final challenges. So how we seamlessly connect Kafka's streaming world with Iceberg's batch analytics world. And we all see the trend, more and more data systems are moving to object storage. It's scalable, durable, and cost effective. So, but just because data lives in the same place like S3 doesn't mean it's easy to share. In most cases, you still need ETL jobs, data format conversion, or complex pipelines to get your streaming data into a data lake. So that breaks the flow. So we believe the next big step isn't just shared storage. It should be shared data. And that's where Apache Iceberg comes in. It gives us a unified table format in the data lake, so different engines can read and write the same data without friction, right? So in AutoMQ, we wanted to make this vision real. We imagine a system where data starts as a stream, like real-time, fast, and open only. And then it's consumed by Flink jobs, Spark streaming jobs, or Kafka applications in real time. And when it's no longer hot, and I mean, if it loses its freshness, it automatically becomes a table ready for analytics without any ETL jobs. So to make this happen, we build something new, table topics. A table topic is not just a stream, it's a hybrid. It behaves like a Kafka topic for real-time consumption, and but also automatically turns your stream into an Iceberg table in the background. So here is how it works. First, we handle schema and catalog management right inside AutoMQ. We have a built-in schema registry, support schema evolution, and integrate with catalogs like AWS Glue, Hive Metastore, and even REST-based catalog service. So as your data changes, the table stays up to date automatically. So second, each table topic has a table coordinator, which always runs with partition 00. It's in charge of managing Iceberg commits, batching them up, and avoiding conflicts, and reducing pressure on the catalog. So this keeps performance stable even under high load. And third, every broker runs multiple table workers. So each worker takes the stream data from a topic and writes it to the corresponding Iceberg table. So the flow is smoothly, data comes in through the stream and gets processed in real time and then quietly lands in an Iceberg table ready for Hive, Spark, Presto, or any engine that speaks Iceberg. So there is no ETL, no manual steps, no complex configurations. So this is how AutoMQ bridges streaming and analytics by bridging both stream storage and the table storage into the same system, the AutoMQ. Yes. So that's our vision of shared data and not just shared storage, but truly unified, accessible, and ready for any workload. Okay, for those who want to go dive deeper, and we have included a few links here on the slide, like from the architecture to Iceberg integration and cost optimization. So everything is online. Just check them out when you get a chance. Okay, that's all for today. Thanks so much for your time. And if you have any question, please feel free to ask now. Also, you can also scan the QR code to join our Slack community. We would love to hear from you. Yeah. Okay, thanks everybody for your time.
Okay, thank you, Xinyu, for the insightful sharing. Okay, now it's a Q&A time. Does anyone have questions? If you'd like to ask a question, you can unmute yourself now and start asking Xinyu. Okay. If we will share Xinyu's slides later through email. Yeah, if you have more questions, you can ask us later. Okay. Now it's sharing shares time, and he will from Decodable, and he will share his insightful content for us. Hi, Sharon, please.
Hi, thanks everyone. Let me quickly share my screen. All right, cool. So earlier we just heard from Xinyu about an incredible story, how they talk about iceberg ingestion. And for my talk, I'll be focusing on a specific processing once the data is already landed in Iceberg. So specifically, I'll talk about incremental change processing with Iceberg and Flink. A quick introduction about myself. I'm currently a head of product at Decodable, but I'm also joined 4 years ago as a founding engineer. So today I'm gonna wear my engineering hat and to really talk about some of the engineering challenges we encountered and while working with our customers. Everything is the solution is open source, so there's no selling of the product. So let's get started. So quickly, what I'm going to talk about today is I'm going to talk about quickly give introduction about how to do incremental change processing using Flink. For those who are not quite familiar with it, Flink is a stream processing engine, so it natively support incremental processing. Here, we'll talk about specific change processing that's related to change data capture, and we'll see how Flink deal with that. The second part is specifically for Iceberg. In order to do incremental change processing with Iceberg, unfortunately, there's no native support from Iceberg yet. Well, there's a need. So how do we solve this problem? I will go through the solution. And just a little hint, it is related to something if you may have heard from the Kafka community. It's called stream table duality. And lastly, I want to talk about the newer development in the Iceberg community. There's a V3 spec that's already out there. It's called rolling lineage. I don't think it's fully released yet, but you can already check it out. And I will talk about how this impacts the processing. Cool. So as I talk about change processing, just set a stage. Normally, this is in the context of change data capture, and the way you think about change data capture is for your operational or like any databases. There can be a lot of operations that are writing into your database. And you can think as there's a change log. So if you read that change log as event stream, you can do a lot of things. So specifically, change stream basically means it gives you all the events of what happened in your database. So if there's an insert or update a record or delete, you should see those events, individual events, as the change stream. When we talk about incremental processing in Iceberg and Flink, there are two parts of it. So one thing is on the reading side. Imagine you have a bunch of Iceberg tables and you want to process it incrementally. It's very important. First, you can read those change events from each table. So what happens to each table? Is there a new record inserted or updated or deleted? You want to be able to read that as a stream of events, change events. And Flink then can interpret those events and do the processing. On the writing side, Flink produce also the change stream, and we'll need to be able to write those stream into Iceberg tables. So here's the context we are talking about, two parts, reading and writing, and Flink in the middle. Hopefully that's clear. So I'll talk about the first thing. How does Flink actually process change events? So here's an example. Let's say there's a simple table with a name and a country code, right? And those events get inserted into your database. Now we see, so the events starts from left to right. I know sometimes it's a little bit confusing. So the first event is we insert Alice US, and then we insert Bob, and then we update Bob. And we run a query in Flink. We basically want to, for each country code, we want to count how many users are there. How does this work? Flink, as we know, Flink process events one by one, incrementally. That's the whole thing about stream processing and incremental processing. So first, you look at insert events. So Alice US, and it immediately outputs the results as it comes in. So it will output an event. Now there's for US country code, there's one user. So you can immediately get that event as soon as this input is processed. And continue, we get Bob. So now we know US should have 2 users. So there's should be 2 counts. How does this work? Flink, this is the main core part of Flink change processing. As you can see, it is able to represent a retraction. What it means is it first emits an update before, basically talking about this is the event I want to retract, and an update after, which with the newer value. So it says, okay, I want to retract the previous US 1, and now the new value for this US is 2. This is internally how Flink represent retraction records. There's basically called row kind, and there are 4 record types. So there's insert as shown already. There's update before and update after. This pair shows the retraction, and there's delete. This imagine, if we need to delete a record, then it's just a delete. For our context here, you can think update before as delete too, and update after as insert, just for simplicity. And I'll use that in later presentation too. Okay, so now we have an update event from upstream. So we update Bob to be in the UK. What happens here? So here we have, we need to retract the previous results for the US again, because now there's only one person, Alice, in the US. So we, Flink would emit another pair of retraction. So US 2 become US 1 again. And now because Bobby is in the UK, we need to add a new record for this country code. So now in UK, we have new record with the 1. Okay, so I hope this give you a good idea of how Flink is processing changes. Again, the key part is it processes each event as it comes in and emit output immediately. And 2, because some records have changes, so it's able to emit retractions so that the downstream operation systems know how to update their systems. Bringing this back to Iceberg, what are the challenges when you use Flink with Iceberg? And yeah, so here I'm talking about Iceberg V2. This is the current released version. As you can see, this is the graph I've already shown you. There are 2 aspects of it. On the reading side, Flink must be able to read those changes to a table as a stream. And on the writing side, Flink must be able to write those change streams to a table. So let's go over each of the requirements. So if you check on the Iceberg website, it's here is a screenshot of the Iceberg doc. You can see Iceberg tables can discover only append only snapshots, and the CDC read here is basically the change stream read. It's not supported yet, so unfortunately, there's no way to directly connect to an Iceberg table and get a stream of change events to that table. So this is unfortunate. And there's another problem on the writing side. So because Iceberg does have upsert table where you can think it as you can write updates and deletes to that table, which is great. But as you can already see, I show you a simple example. Three events that come in produce like 6 records. So you can see there are a lot of output events. There's definitely more output than the input in most of the cases. So when that comes into writing to data lake, which is notoriously not very good at handling tons of updates, there are lots of performance issues. One, Flink use equality deletes. If you're not familiar, basically it's saying if you want to represent a delete in Iceberg for Flink, it's it just writes a record saying, okay, this is a delete. I want to be this is a record I want to delete, and it's the reader of that table needs to figure out when it's reading the table, it has a record of all the deleted records, and it needs to do the merge. So you can see it's very, very slow for the query time when you have tons of deletes, because for each delete record, you need to go through all the rows in the table and figure out which ones you need to be needed to be removed. So very slow for queries. And also, as you can see, because there are a lot of retractions, those essentially are delete records. Like I said, update before is delete, and there's also delete. So there are tons of delete records that will generate a lot of delete files in Iceberg. So quickly, you can see all those files, small files pile up, and you get to this small files problem. And again, that further reduce the performance on the query time. So this is not good. So as a result, it feels like, okay, change stream processing is probably doesn't really work in Iceberg v2. And what do we do? It feels like there's nothing to do. But of course, you guys are here not because just you want to know this. You want to know the trick. So here's the trick. I spend a lot of time in the Kafka, dealing with Kafka and Flink. So I know there's very good story between integration between Kafka and the Flink. So I know change stream processing is pretty easy, and if you use Kafka and Flink. So can we do something similar to mimic the Iceberg tables as a Kafka topic? So that's where the trick comes in. So at a high level, there are two parts of it. So first, we can store those change events in append tables. So you can think those append tables as basically an audit table, or like a table with all the change events. So instead of materialize those change events in an observer table, you just put all the events in the append table. And I'll show you exactly how to do that. And then you can merge and materialize in the append tables on read. So basically, compact all the changes when you are reading your table, and then you get the materialized results. So normally this is called stream table duality. I know it's a little abstract here, so I'll go through an example. Again, so how does it work? We are going back to the example I already showed you. So we have a country code and count from those tables. And now we're adding, those are just like additional metadata we want to add. We're adding a timestamp. And the main thing here is I'm adding a new column is deleted. And this column will tell us if a record is being deleted or not. So you can think as I'm just going to write the events to the table instead of writing to a delete file. Okay, here we are using some Flink API to do this kind of processing. There's nothing fancy here. The main thing is if you're not familiar with Flink APIs, just focus on the overall processing. It's Java code here. So what we are doing here is we are mapping, we're just using Flink API to map that SQL query into a stream. So this is standard Flink stuff. And while we are adding this specific new processing to set the is deleted column, right? As I said, update before and delete. Those are retraction records, and those are the records we want to delete per the processing. So now we are setting this is deleted to true once we get a record that has this metadata, Flink internal metadata that's updated before or delete. So now with that, you can write this result, a stream of events, into a append table. Yeah, so there's nothing fancy. It's just like how you create another stream and write to it. As a result, let's just look at the example. Those are the events we talked about before, right? You have insert, and update after, and all that stuff. This all get into the Iceberg table. So instead of we have like 2 records, US and UK, that already materialized, we are writing all of the records into the Iceberg table. And we have this is deleted column that shows which one is deleted. So with this, how do you query it? It's actually pretty simple. You can use like any of the query engines. The main thing is while you are querying that table, you need to find the latest value per key, right? So this is an example of a simple query, how you find each country code, the latest value of each country code while you are querying the table. And of course, like you don't want to get any deleted records, so you can filter it and find the row number equals 1, which means the latest value per that country code. And now with this input, you will be able to get the exact value you are looking for. So there's 1 in the US and 1 in the UK. So I know you are kind of thinking about this. What about the query performance? Because you are like writing a lot more records in the table, and there are more and more records to merge at the query time. And we talk so much about query performance. What about this? It doesn't seem like this is better. And I'll say it is more work for the query engine to query. For sure, there's some trade-off here. It's actually not too bad if your table is small, because querying a pen table without going through all those delete files is actually not bad. It has pretty decent performance. But really, like, what if we want to optimize the performance? And if you are familiar with Kafka compacted topics, you'll think about, can we do the similar thing as Kafka compacted topics in Iceberg, since we are already mimicking the Kafka behavior here? So it turns out, yes, we can do this. So the way to do it is Iceberg has all those snapshots while you are reading, whenever you are committing your data to Iceberg, a new snapshot is created, and all the data is partitioned. So an example is at a high level, you can do the compaction, like knowing some part of the data is already old. A lot of this is event time processing. So we have, as earlier I've shown you, there's a timestamp we added. So some of the data is already very old, and your current writer will not touch those data. And if you partition this nicely, you can here as an example, you can have a partition of month 1, and your current Flink writer is writing to the month 2. Nothing will change for this partition 1 anymore. So you could run a batch job that basically compacts all of the change events in month 1 into a separate partition, so that now on the query side, the data it needs to go through is way less, right? So basically you compact or materialize all the change events in old partitions in here, partition 1, into a merge partition. And you can still keep your stream writers writing to the current month. They will not conflict. This is very nice, nice treat about snapshots. So once you merges the partition 1, when that is done, you can just overwrite. You delete this snapshot 3 and merge those changes into a special partition. Here I'm using 0. So you are using the merge partition 0 to have all the old already compacted events. And once you delete this, you have now the snapshot 4, which is very clean. you can when you are querying the table, you can just query the latest snapshot 2 and 0. So partition 1 is gone. It's there are waitlist data to read, and you can continue to do the same when the stream writer goes to month 3. You can merge and compact all the events in month 2 and put into this merge partition 0. All right, so putting it together, basically we are using Flink in 2 ways. You can use a stream processing job, continuously read those events from those Iceberg tables because we are storing them as append logs. So you can directly just read those tables as events and interpret those changes in your stream processing job. And on the writer side, you can write those events as basically append logs into an Iceberg table, and you can separately run a batch job to merge those changes to compact for better query performance. Okay. So that's kind of like the workaround you need to do for Iceberg v2. There's a lot of passion in the community because of all the needs of real-time processing and the need for change processing. So definitely a lot of discussions about how Iceberg can support this better. As you can see, I presented you a workaround. As an engineer, no one is really happy with workarounds. Are there better ways to solve this? So this brings us to the next topic. So Iceberg v3 has a new feature called row lineage. What is it? So lineage is tracking changes to individual rows as they are updated, deleted, or inserted. This sounds great, right? It sounds like, okay, now we are getting all the changes to a table like per row. That means we can get all the changes of a table. And that's the foundation for incremental change processing. So this is great. But there's a special thing about, if you remember, I talked about Flink use equality deletes. And row lineage currently doesn't track for row updates that are written through equality deletes. So this is unfortunate. The reason for this is because for Flink writers, those kind of writers that are highly optimized for writing performance, tracking the additional changes per row means there's a lot more work to do. That basically means when you are writing an update to a table, you need to know what is the value for the previous row in order to track the changes. So for Flink, a lot of times I would say by default, it's optimized for writing performance. So it will eagerly write, okay, this is a record I want to delete. So it doesn't want to go check, okay, where is the row I want to delete. It just output, okay, this is the row I want to delete without tracking the previous values. So natively, this is not tracking the row lineage if you are using quality deletes. So what does this mean for Flink? As I said, Flink is not using equality deletes, so it's not tracking. So I think the solution is not obvious. I think there's a trade-off to make. I think Flink and a lot of other processing engines needs to track. In order to use this, needs to track, keep the state of all the keys, all the rows, and be able to use I think delete vector in v3 or positional deletes in Iceberg v2 so that it can track the row lineage information. And on the writer side, the row lineage only gives you the foundation framework of how to track row lineage, but it doesn't automatically give you a stream of changes. So some work needs to be done to derive a stream of changes while you are reading a table from the row lineage information. So you can think as row lineage information is additional data that's stored with the Iceberg table that tells you, okay, this row is updated. But in order to read that as the stream of change events, this is still on the processing engine side. So as far as I know, there's no development yet for this. And again, everything is early. So TLDR, the framework is there, the row lineage, but the solution is not ready yet. And I would like to see how the open source community make proposals and makes this much easier. Okay, so I think so far so good. Let's wrap up. So key takeaways, I talk about Iceberg v2 and how it supports incremental change processing. It needs workarounds. We are using the stream table duality to solve this problem. So you write change stream to append only tables, and you can read those append only tables and interpret that as a change stream. And for query performance, you can use the batch merges to compact all those retractions. And I talk about Iceberg v3 row lineage can make it easier, but still needs more development so that the processing engines can actually read a stream of changes, derive a change streams for processing, and also there's some limitation on the equality deletes. Okay, cool. So that's it. Thank you, everyone. And feel free to follow up with me if you have any questions after this by finding me on LinkedIn. And if you have any questions here, feel free to unmute yourself and ask.
Okay, thank you for sharing the insightful sharing. And I see John have a question. Can you see it on chat box? And John, you can unmute yourself if you want to talk with Sharon. Okay.
Oh, I see it's about schema changes. Yeah, so it's definitely there's a bunch of limitations. Schema changes is a whole different process that requires a lot of operations and maintenance work. So normally, if there are stream changes, then this is not just for Flink or Iceberg. For on the processing side, whenever you are processing something that has a change schema change, if it basically means you need to the person who is developing the business logic of like how you process the data needs to make a decision of how you want to handle that schema change. So it could be you need to stop the Flink job and rewrite the logic to account for the schema changes, right? Like to add the new rows, to remove the rows that's already deleted, whatever the changes, it happens there. And also it can also be something you set on the organization level, right? Like your table is guaranteed to not have backward incompatible changes so that you don't impact the downstream processing. But in general, this is a decision to make at the application level, like how to handle the schema changes. Let me know if thank you. Yeah.
Okay. Does anyone have more questions? And I can have a question, maybe a little bit off the topic. I'm just interested in about the differences between Python and the Iceberg table. Yeah, we see that there are some problems in the Iceberg table v2, and I want to know how to choose in the real scenarios when we need to use these tables format. Can you give us some advice about it?
Yeah, thank you. Thank you for asking. I'll say I have a lot more experience with Iceberg. I did some reading about Python, so this is it can be outdated, but I can say this for sure. Python is designed more natively to support stream processing. Python is works very closely with Flink community to support. I think a lot of you have heard the streaming lakehouse architecture. So Python has more native support to provide the changelog for Flink to read. I think the implementation is just like it writes to, if you have updates, it writes to an upsert table, but there's also a streaming storage that contains the changelog, so you can directly read the changelog from to get all the events from all the change events from that table. So I would say this would be a lot easier if you use Python. I've never used it in practice, so I don't know. I can't talk much about the scaling factors, the performance, the reliability, those kind of things. In terms of community, I think I'm from the Bay Area, so like I can talk about the US market. I see a lot more people using Iceberg. I think it's just because it's backed by Snowflake and Databricks, all those large companies. Python is probably more popular in Asia and Europe.
Okay, thank you very much, and makes sense. Okay, does anyone have more questions? Okay, and I'm very happy that you guys can attend this meeting and live till the end. Yeah, very thankful. And later, if you are interested in these videos, and we also can share this slide for you through emails. And I hope if you have many more questions, you can find us on LinkedIn, Xinyu and sharing, and ask more questions with us. And you can also join AutoMQ and the Decodables community. Yeah, thank you everyone. See you next
Thank you,
time.
everyone.
Thank you everyone. Bye bye.
Bye bye.
Bye. Have a good day.